a recording going on already or not. Okay. Yeah. All right. What?
Did you do that on that deck?
Yeah. Beamer, yeah.
That's so disgusting. I mean, I respect it.
Disgusting.
Whoa.
That's a strong word, you know?
Actually, I hate
That's
latex
great
too.
effort. Great effort. Yeah.
Hey, latex is turning complete.
LaTeX is great, especially for like bibliography stuff.
All right,
It's like-
next we have Luke Proctor talking to us about Galois Theory. Let's
Yeah.
Luke.
I'm gonna do my best. Hi everybody, so today I'm going to be talking to you about Galois Theory. This is a really important topic in higher level mathematics, especially like in terms of abstract algebra, especially when it comes to finding out facts about fields, polynomials, and things of that nature. For this presentation, I'll be trying to go over some of the history, because I think Galois' life is kind of infamous for being pretty interesting, so to speak. And then I'll be trying to go over like a quick overview of some topics in abstract algebra that would be kind of necessary for getting an understanding of Galois theory. And then I'll talk a little bit about the Galois correspondence, that's the fundamental theorem of Galois theory. And then I'll briefly touch on some different aspects of mathematics that Galois theory is useful in helping us find out more about. So the history of Galois theory, I think we should start with the problem that Galois theory is actually trying to solve. So when it comes to Galois theory, one of the big problems that Galois theory was looking at finding the solution to was the solubility of polynomial equations of certain degrees. So it starts back in Babylonian times, really. We have some clay tablets that actually give the description or like an algorithm on how to solve quadratic equations. And after that, we wouldn't really have a solution to a cubic equation, the equations of degree 3, until about the 1600s through Cardano, originally discovered by Galois Theory, but published by Cardano. There is some rumors about a Spanish mathematician who found it and was burned by a Spanish general because learning the solution to a cubic equation, I believe, was something that only God should know. But this is this is something that's actually kind of disputed historically, so I'm not really certain about that. So in the early 19th century, early 19th century, and well, technically 1799, Ruffini came up with a solution to the to whether or not a quintic equation or equation of the 5th degree was able to be solved. But people didn't really believe him at the time, and he also had a little gap in his logic that didn't really fit well with the mathematics community. But Abel was able to prove it in full, although it wasn't entirely accepted at the time. But at the same time, or at a similar time, so Galois was born in about 1811 or so, and at this time he was, starting to grow up and becoming a mathematician. So next we'll talk a little bit about Galois. So he was born into a political family. His father was actually the mayor and a Republican. Republicanism at the time in France was a political movement related to taking down the monarchy that was ruling over France. And then his mother would actually educate him for the first 12 years of his life, and then he would move on to go to a preparatory school. Over here in the preparatory school, he didn't really have a whole lot of interest in learning the subjects they were teaching him. He kind of had the gifted child syndrome, so to speak. But during this time, the amount of time he gained by ignoring his classes, he would use reading Elements de Géométrie by Adrien Marie Legendre, This was a book about non-Euclidean mathematics, and it would be kind of one of the fundamental books that helped him to grow as a mathematician. So one of the big aspects of Galois' life is that he actually submitted 3 different papers relating to his fundamental theorem on Galois theory. One of them was going to be for a big mathematics prize, and it was ignored. Then there was another paper that was submitted, and it would be eventually rejected. He was trying to get into one of the biggest mathematics schools in Paris, the École Polytechnique. Yeah, it was one of the most prestigious academies in France. One of the issues was that because a lot of the mathematicians over at the Polytechnique were actually engineers, Galois' theories were a little bit too abstract for them. So they would go over to him after he had his submitted his paper, and they would say to him, "Oh, I am French, and I find your paper very interesting, but there's not very much application for me. I would appreciate it if you had more examples and more applications of your theory." And Galois would respond as saying something along the lines of, "I cannot believe that you said this to me. You are treating me like a quadrator. You have disrespected my work. I have spent so much time on this. I hate the university, and I hate all of the professors there." Something along those lines. It's probably what went on. But regardless, Galois would unfortunately not be accepted into the École Polytechnique. It wasn't necessarily because his papers were bad or they were lacking in mathematical interest, but the issue was, like I said, this general habitus that existed within the system that didn't allow for him to really succeed with the standards that they had there. So the big thing that really killed Galois was actually him dying in a duel. He would have really been a very well-known big mathematician. I think he might have rivaled Euler in some sense if he stayed alive. But unfortunately, Galois had his first and only love affair with a girl named Stephanie, and it didn't go very well for him. We know that Galois wrote some letters to Stephanie, and that there were some exchanges of love letters between the two, where Galois would say things like, "Dear Stephanie, you are my happiness, you are my joy, I could not live my life without you." And then Stephanie would write beautiful letters back to him saying, "Whatever you believe happened between the two of us never happened. And if it did, then it was a terrible, terrible mistake." But, so eventually that didn't work out too well for him, especially because Stephanie had taken a new lover, and, well, this is kind of the general consensus on what happened. There's some kind of speculation on what really went on behind it, but the general consensus is that this issue with Stephanie was somehow involved, and Galois would go over to Stephanie's lover and say, "I love Stephanie, and you must leave her." And he said, and he would probably say something the Stephanie's lover would probably say something along the lines of, "Well, Stephanie obviously has no interest in you, and I am with Stephanie now. So the only logical way that we can solve this problem as two Frenchmen in the 1800s is by a duel." And so Galois would spend the rest of the night before the duel writing a letter, infamously, over to one of his friends named Chevalier. And this kind of condensed all of his mathematics into one comprehensive work. He cleared some things up, added some things that weren't actually in the papers that he submitted before. And he would go on to do this duel. They allegedly, there's an article that says something along the lines of that these two men were very good friends. They couldn't do like an actual duel where they like walk away and then turn around and then like do the shooting thing. So what they did is they actually blindfolded themselves. They took guns. One of them was loaded, one was not loaded, and so they just left it up to chance, shot each other, and then Galois was shot in the stomach and then died a day later, which It's pretty unfortunate. So in order to talk about Galois theory, I think there's a couple fundamental things that we need to talk about first. And so the first thing I'm going to talk about is groups. Groups can be thought of as like different types of symmetries between objects. One of the most fundamental groups that you would have is the permutation group. So it's the group of like permutations of some set of numbers. And this is like one of the really fundamental parts of Galois theory. This would be a alternating group 3 or something. There's 1. So you have like a group of some number of elements, like 1, 2, 3, 4, 5, blah, blah, blah. And then you have different types of subsets that you can make with these groups. I think one of them should be like 1, 2, 3, 4, and then 5 is the identity. And these kind of relate to different ways that you can permute different objects. One of the really nice groups that's very easy to kind of visualize and understand what groups are talking about is the dihedral group 4. So you can think about this as points on a square, and the symmetry is on the square, where you can flip the square or you can rotate the square, and this is kind of like the general idea behind the group. Over here is a formal definition of a group. So it's a group of objects or elements S. It's a set of elements S combined with a binary operation defined for all x, y, z, such that you have this operation or any element in the set are in G or in the group. The sets are the operation is transitive. There's an identity, and from the right side and the left side it equals x. And then for all elements in the group, you also have this property of. Oh wait, that's an abelian. Oh no. There's the inverse. This is the inverse over here. So if you think about y as the inverse here, there is an element y such that x times y is equal to y times x, which is equal to e. So that's a definition of a group. Then we have this other idea called rings. So rings are like a kind of 2 pairs of operations combined with a set. So you have this operation S plus, and that's an abelian group. So this is essentially, you could think about this as just like elementary arithmetic, and then you also have S times. And this doesn't have to be a group, it doesn't need inverses technically, but it satisfies operations closure and associativity. And you also have if you have A times B plus C, it translates to A times B plus A times C. That's a distributive property. So these are kind of the operations that you kind of learn in elementary school. It's a very formal way or abstract way of thinking about those elementary operations. So then another really important idea is quotient rings. Quotient rings are essentially a way of like a fancy way of doing modulus. So if you have a set of things that is the ideal, you can do this operation circle plus on them. And if you have A plus an ideal and then B plus an ideal, then you can pull the ideal out of the whole number, and then just think about the numbers there, and you can create equivalency classes through this process. Similar to how you would create equivalency classes with modulus like remainders and stuff like that. Okay, this is pretty abstract stuff. So fields are kind of like rings, except for you can also do inverse multiplication to them. So you can think about this as just having the field of, well, I mean, the smallest field I know of is, that isn't like a modulo field, would be the rational numbers, so like A over B, any numbers of that form combined with your typical plus and times would equal a field where A over B and then B over A would be the multiplicative inverse, and then all of your other rules of standard elementary operations work there. And then another important aspect of Galois theory here is polynomials. polynomial fields. So a polynomial field is a set of all polynomials with coefficients in the base field. So if you have any kind of polynomial c, or like x to the n plus cx to the n minus 1, c1x to the n minus 1 dot dot dot, or actually, let's just do cn minus 1, and then up to c1. That would be the field of all polynomials where all these cn's are in whatever the base field is. So in this case, you can think about it as the rational numbers here. So an example of a polynomial that's in the quotient field, or the polynomial field of the rational numbers would be x squared minus 2. X squared 2 would be a coefficient that's in the rational numbers, and then you also have 0 here. So you could have x squared plus 0x minus 2. All of those coefficients are in the rational numbers. But if you split this polynomial, you have x minus square root of 2, and then x plus square root of 2. And that's obviously not a rational number. So, and then you also have field automorphisms, and this is one of the kind of more difficult things I'm going to talk about too here. So field automorphisms are ways that you can perform a function to a polynomial that's order preserving. So you have an isomorphism, and then this function, it maps the field to itself. It doesn't change it. In the context of Galois theory, we can kind of think about, and within polynomial rings, we can think about this as changing the roots around in different ways within a polynomial. So if you have so if you have like a polynomial here, x minus the cube root of x, or the cube root of 3, and then x squared, there's a equation with a cube root of unity in it. Cube root of 3x plus cube root of 3 squared. There's a way to kind of shift around these polynomials in such a way, or the roots of this polynomial here, in such a way that this polynomial is going to remain the same. But if you were to like shift this root over here and then swap one of the roots in this equation over here, that would no longer be an automorphism of that field, if that makes sense. And that's kind of what I talk about on this slide here. So yeah, with that previous example, we have symmetric polynomials, which all the coefficients of a polynomial are symmetric polynomials of the roots of a polynomial. So here we have the roots of a previous polynomial are x minus the cube root of 3. Then you have x minus the cube root of 3 w, or omega, which is when omega is a cube root of unity, which means that if you have a unit circle, essentially, then this is like one of the points on that circle that divide the circle up to 3. The big important thing to remember about these is that 1 plus a cube root of unity plus a cube root of unity squared is equal to 0. And then you have a final polynomial here, cube root of cube root of 3 omega squared. So if you look at this polynomial right here, remember that this polynomial, when you multiply it all out, it just equals x squared, or x cubed minus 3, right? So if we were to perform some operation on it such that 3 and 3 times the cube root of unity to the first power, if we just swap those two around, then we still have the same polynomial here. We haven't really changed anything about the field itself. And this is kind of the general idea about Galois theory. We want to do these automorphism operations, and then we start to create expansions to the field where we take these polynomials apart, and we can't do the same exact operations on the polynomial without breaking the field in some way. So with that, field extensions are another very important part of Galois theory. And they're normally made with quotient rings. So like we were talking about earlier, so if you have like the rational numbers and then you extend the rational numbers with the cube root of 3, that extended over Q is a quotient ring. And so we can create a basis of so we can kind of think about these field extensions as linear spaces or linear combinations of roots and the kind of bases of the linear combination, or we can think about them as a basis of a linear system, I believe. And you can construct a field for like a given polynomial by putting its roots in to the field, and then trying to keep expanding that field out. And then when you see linear combinations of the roots that are the same, you can just use one of the roots instead of all of them. So yeah, it's linearly independent combinations of basis elements. Yeah, so we can also write elements in terms of a basis of a field, and that helps us to find automorphisms as well. So yeah, we have these things called fixed fields. So you have a fixed field of E under a given automorphism. You can also have a set of automorphisms together, and you can create a fixed field under the set of automorphisms that keep the field fixed. So fixing of a field means that essentially if you have any element of a field, so like A in a field, phi of A is just going to still be equal to A. So with this definition right here, this is a really important definition. If you have just any set of automorphisms and those automorphisms leave some field fixed, then it's called the fixed field of E under S. And if we have an extension of F, which is extended by E, the group of E over F consists of the automorphisms of E, which leave every element of the group fixed, and that group is denoted by E over F. Then we also have normal and conjugate extensions. So if you did any group theory, these terms will be familiar to you. A normal extension is, or a normal group in group theory is a group where you have an element in the group A, and then if we have a group G, or actually let's just say G, little g, G inverse. Oh wait, actually let's make that H. So let's say H is a subgroup of G. Then G inverse, or GH, G inverse is in G, or is in H, my bad. And you also have conjugate extensions, and in group theory we also have that if H1, H2 are subgroups of G, then G, H, G inverse is in H2. So this is like the definition of a conjugate group. And there's similarities, as we'll see, between these conjugate groups and conjugate extensions, where conjugate extension, if you have a sigma that goes to K1, then it goes to a field K1, then it is a conjugate of K2 because it equals K2. So here we have the fundamental theorem of Galois theory. So if you have a polynomial P of x and f of x that's separable over x, separable just means that there are no repeated roots within the polynomial. Then E is a splitting field of P of x, and you have three intermediate fields that we label K, K1, K2. Then what the fundamental theorem of Galois theory states is that there's a one-to-one correspondence between K and G, and that's only true if K is equal to the fixed field of G. And so G is our Galois group, right? And then K is our intermediate field. So if we have some group G, or subgroup G, and K, and G is a group of the automorphisms, then K is equal to a fixed field of G. And then G2 is a subgroup of G1 if and only if the field fixed by G2 is a extension of the field of G1. And then K1 and K2 are conjugate subfields if and only if the field fixed by, or the group of automorphisms fixing K and the group of automorphisms fixing 2 are also conjugate subgroups. So you go back to this right here. You have these conjugate subgroups, and they correspond to these subfields in this particular way. And then you also have normal extensions. So if you have a normal extension of F, if you take all the automorphisms, or K, normal extends F. If you take all the automorphisms that fix K, they are a normal subgroup of all the automorphisms that fix F. And then if F is a normal subfield of K, then we also have this fact over here that the group fixing the automorphisms the group fixing the field K over F is a isomorphic to the quotient group of the automorphisms fixing F over the automorphisms fixing K. And then finally, we also have this fact over here that the dimension K of F, so if you remember from linear algebra, it's kind of similar notation for the dimension. How many basis vectors or how many bases or elements are in the basis for our vector field? This is equal to the number of left cosets of G over F, and or I think it's indexed as a part of O. And then also the dimension of E over K is equal to the number of elements in our group fixing K. So E is like our splitting field, remember, so it's the field that makes all of these kind of roots possible to put into this form here. So this is all fine and dandy and very confusing, but how exactly does this help us? So one of the ways that this can be interesting, and we can apply it to maybe our everyday life, probably not, but not normally. But if we have a equation of some certain degree, we can find out things about the fields that the equations live in by using facts about their Galois group. And so one of the big things that Galois solves with his theory is whether or not you can solve an equation of degree 5 or greater. And he does this by showing if you have a group that's solvable, there exists we have this concept called solvable groups, which means that you have a finite sequence of groups that of normal subgroups that reach the identity such that the quotient group of g of I over g of I plus 1 is abelian, or the quotient group. And then you also have this idea of solvable fields. It's a pretty long definition, but essentially it's just saying that all of the roots in the field exist in the field as roots, and you can pull them out of the field as you go. Then we have another theorem that if f of x is solvable, if a polynomial is solvable, and E is its splitting field, so we have a polynomial that's split by this field E, then the group is solvable. So if we want to know if we can solve a polynomial, all we have to do is find out what its Galois group is, and if that Galois group is solvable, then we can find a solution to it without any kind of, well, at least while using radicals specifically. So then over here we have this theorem that says that if we have a generic polynomial with linearly independent coefficients here, or algebraically independent coefficients over f, then we have a group of the equation that it's the symmetric group of S of n, and this leads us to the proof that equations of degree 5 or greater are insoluble by using radicals, because the group S of 5, or the symmetric group of 5 elements, is not a solvable group. So for further research that I would like to do, there's an unsolved problem in Galois theory called the inverse Galois problem, and I'd like to keep studying Galois theory over time and try to figure out more about it, become a little bit more familiar with it. But I would also like to try to observe this kind of this problem a little bit and play around with it. So the inverse Galois problem, which this asks whether or not there's a finite group that appears as a Galois extension of the rational numbers. And then there's a lot of other interesting facts that you can look at with Galois theory. There's a lot of further applications. Some things are such as whether or not you can find out if, or whether or not you can construct a polygon with a ruler and compass is one of the things that Galois theory can show. And it turns out if you have a Fermat prime of 2 to the 2 to the m plus 1, so if this number right here is prime, then you can construct it theoretically if you want to take out the time, because sometimes these can get very large. You can construct a polygon using a ruler and compass method. And then, I guess that's all I really have for right now.
Thank our speaker.
Yeah, so here's my references.
Questions for our speaker?
Yeah, sure.
What does it mean for a group to be abelian?
For a group to be abelian? Oh yeah, my bad. I didn't really touch very well on that. So an abelian group is a group which all of the elements satisfy the commutative property. So if you have an element in a group, S is in A, or wait, whoa, wrong way. You have A and B in S. For any A and B in S, A times B is equal to B times A. If that's true for all of the elements in the group, then that's an abelian group. Yeah.
Other questions?
So in this duel, if only one of the guns were loaded, why did they do it blindfolded?
I don't know. I don't. Maybe that was a little bit of an elaboration on my part, but that's just adding to the tradition of speculating on the death of Galois, I suppose. Yeah.
I'm curious, you talked about the Galois theory
Yeah.
and how this corresponds. Do you have an example of
the
fields and groups and how that corresponds?
Oh, are you talking about the lattice structure of it?
Yeah. Do you have an example of that?
Is there a chance I could pull up my paper and then I could show? Because I have an example of it in my paper.
My battery's about to die.
Oh, yeah. I do have an example of that in my paper. I just kind of felt like my presentation was probably going to be a little bit too long, and I didn't want to like have to explain how subgroup lattices and stuff worked. But yeah, I mean, I can show that whenever DeLong gets back and can access the thing. Yeah. I'm sorry, that was probably really confusing. I had to go. I had to try to go. I didn't actually, but I had to try to go through 2 semesters of abstract algebra in about 20 minutes. So if you could be a little bit forgiving.
I have a question.
Yeah.
Were those hats that were
Yeah,
Velcro?
my mom made these.
I am so impressed. Oh my goodness.
Yeah. I was kind of unsure about whether or not I wanted to do the sock puppet thing because I knew I wasn't going to have a lot of time, but my mom made them for me already. So, like, I couldn't not do it. That'd be disrespectful to my mother, So.
All right, let's thank our speaker again.